At 11:27 hours on January 9, 1945, Warrant Officer Sadamu Komachi sits strapped into his Mitsubishi J2M Raiden at Kisarezu Air Base, 40 kilometers southeast of Tokyo. Four Boeing B-29 Superfortresses approach from the southwest at 8,500 meters altitude. Air raid sirens began wailing 6 minutes ago. Komachi receives takeoff clearance. He advances the throttle on his Mitsubishi Kasei 23 14-cylinder radial engine to emergency war power, 1,820 horsepower at 2,750 revolutions per minute. The Raiden accelerates down the runway. Gross weight is 3,347 kilograms. Wing loading is 197 kilograms per square meter, the highest of any Japanese fighter in operational service. Liftoff speed is 168 kilometers per hour. Komachi rotates at 173 kilometers per hour and climbs at 19.4 meters per second. 6 minutes and 47 seconds later, he reaches 8,500 meters altitude. He is now above the B-29 formation with 300 meters altitude advantage. Komachi rolls inverted and pulls through into a 70-degree dive. Airspeed increases to 630 kilometers per hour. At 400 meters range, he opens fire with 420mm Type 99 Model 2 cannons. Combined rate of fire, 2,400 rounds per minute. Each shell weighs 128 grams. He fires a 2-second burst. Total projectile weight, 102.4 kilograms, striking the target area per minute of firing. The lead B-29's No. 3 engine explodes. The bomber drops out of formation, trailing smoke. Komachi's closing speed is too high. He overshoots, extends for 3 kilometers, and climbs back to attack position. By the time he completes the maneuver, the remaining B-29s have adjusted course and increased defensive spacing. American gunners now track him continuously. Komachi attacks again from the forward quarter. Return fire strikes his canopy and right wing. He destroys a second bomber, but his engine begins running rough. Oil pressure drops. He breaks off and returns to base. 2 B-29s destroyed. 1 Raiden damaged, requiring engine replacement. Komachi is uninjured. This engagement typifies the J2M's operational career. Devastating firepower, excellent climb performance, and marginal reliability. The Raiden was designed to kill B-29s at altitudes where the nimble Zero could not operate effectively. It succeeded in this mission when it functioned properly. It functioned properly less often than required. The story begins in 1940 with expectations that proved entirely wrong. The Imperial Japanese Navy recognizes in mid-1940 that future air combat will occur at higher altitudes and speeds than current operations. The Mitsubishi A6M0 dominates combat at altitudes below 6,000 meters through superior maneuverability. But intelligence reports indicate American and British air forces are developing heavy bombers operating at 8,000 to 10,000 meters altitude. The Zero's engine, optimized for low altitude performance, loses power rapidly above 7,000 meters. At 9,000 meters, the Zero struggles to maintain 380 kilometers per hour and cannot effectively pursue bombers. The Navy requires a dedicated interceptor capable of reaching high altitude quickly and delivering sufficient firepower to destroy heavy bombers. Unlike the Zero, which emphasizes agility and range, this new fighter should prioritize climb rate, speed, and armament. Range can be sacrificed because the aircraft will operate as a point defense interceptor from airfields near cities and industrial areas. Maneuverability can be reduced because attacks on large bombers require only brief periods of precise flying for weapons delivery. The Navy issued Specification 14 Sure to Mitsubishi Heavy Industries in October 1940. Requirements specify maximum speed exceeding 590 kilometers per hour at 6,000 meters altitude. Climb to 6,000 meters in 5.5 minutes. Ceiling exceeding 11,000 meters. Armament of 2 20mm cannons and 2 7.7mm machine guns. Range of 1,185 kilometers. These specifications demand revolutionary design for Japanese aviation. No Japanese fighter has achieved 600 kilometers per hour in level flight. No Japanese engine produces sufficient power at high altitude to meet the climb requirements. The armament weight exceeds anything previously installed in Japanese fighters. The entire specification assumes technology and manufacturing capability that Japan does not yet possess. Mitsubishi's chief designer, Jiro Horikoshi, creator of the Zero, assigns the project to a separate team led by engineer Yoshitaka Tojo. Tojo examines the requirements and concludes that conventional approaches cannot succeed. The Zero achieves its performance through minimal weight and maximum aerodynamic efficiency. The new fighter requires the opposite philosophy: maximum power and maximum firepower regardless of weight and drag penalties. Tojo designs an aircraft around the most powerful engine available, the Mitsubishi J2M, a 14-cylinder two-row radial producing 1,430 horsepower at takeoff. This engine weighs 590 kilograms, 200 kilograms heavier than the Zero's Nakajima Sakai engine. Its frontal area measures 1.27 meters diameter, creating substantial drag. Tojo accepts these penalties as necessary for achieving the required performance. To minimize drag from the large engine, Tojo designs the fuselage with minimum cross-section behind the engine. The cockpit sits directly behind the engine cowling, giving the pilot restricted forward visibility. The fuselage tapers sharply to a small tail section. Wings are short and straight with relatively thick airfoils optimized for high speed rather than maneuverability. Wing area is 17 square meters compared to the Zero's 22.44 square meters. This reduces drag, but increases wing loading dramatically. Armament installation presents challenges. 420mm cannons require space, ammunition storage, and structural strength to absorb recoil forces. Tojo mounts 2 cannons in the wing roots and 2 in the wings themselves. Total ammunition capacity, 800 rounds, sufficient for approximately 16 seconds of firing. The weapons installation adds 283 kilograms to empty weight. The prototype, designated J2M1, flies in March 1942. Test pilot Katsuzo Shima reports serious problems immediately. The aircraft exhibits severe vibration at all speeds. Control forces are excessively heavy, requiring significant pilot strength for maneuvering. Visibility from the cockpit is restricted to the point of danger during takeoff and landing. Engine cooling proves inadequate, causing overheating during climbs. Maximum speed reaches only 537 kilometers per hour, well below the required 590 kilometers per hour. Investigation reveals multiple design flaws. The propeller, a 3-blade unit designed for lower-powered engines, cannot efficiently convert the Keisei engine's power into thrust. Vibration originates from the engine mounting structure, which lacks sufficient rigidity. The cooling system's air intake design creates turbulence, reducing cooling effectiveness. The wing root cannon installation generates aerodynamic interference, increasing drag. Mitsubishi initiates modifications. The propeller is replaced with a 4-blade unit increasing diameter from 3.0 meters to 3.3 meters. Engine mounts are strengthened and vibration dampeners added. Cooling system ducts are redesigned. Wing root fairings are modified. These changes add 68 kilograms to empty weight and delay production by 11 months. The revised prototype, J2M-, flies in October 1942. Performance improves. Maximum speed reaches 587 kilometers per hour at 5,700 meters altitude. Climb to 6,000 meters requires 6.1 minutes. Service ceiling extends to 11,800 meters. These figures nearly meet specifications. And the Navy orders production. Production aircraft begin reaching operational units in December 1943, 3 years after the initial requirement. By this time, the strategic situation has changed completely. American B-24 Liberator bombers raid Japanese positions throughout the Pacific. American carrier aircraft attack shipping and installations with impunity. The Battle of Midway has destroyed Japanese carrier striking power. The Solomons campaign bleeds, experienced pilots faster than training programs replace them. Japan needs fighters desperately, but it needs them for combat at all altitudes and ranges, not just high-altitude interception. The Raiden arrives optimized for a mission that represents only a fraction of actual requirements. It climbs quickly to high altitude but cannot escort bombers on long-range missions. It carries devastating armament but consumes ammunition in seconds. It achieves high speed but handles poorly in the turning fights that characterize Pacific air combat. It represents exactly what the Navy requested in 1940 and almost nothing the Navy needs in 1943. Operational deployment reveals additional problems. The Kasei-23 engine, finally available with improved supercharging for high-altitude performance, suffers persistent reliability issues. Valve failures occur frequently. Oil consumption exceeds design specifications. Cylinder head cracking develops after 40 to 60 hours operation. Mean time between engine failures averages 73 hours, less than half the Zero's engine reliability. These failures prove catastrophic for an interceptor. Pilots scrambling to intercept incoming bombers cannot afford engine failure during climb. Yet this occurs with alarming regularity. Between January and June 1944, the 381st Kokutai at Opama Air Base loses 17 Raidens to engine failures during takeoff or initial climb. Only 3 of these pilots survive. The unit's combat effectiveness suffers accordingly. Maintenance requirements, compound availability problems. The Raiden requires 22 man-hours of maintenance per flight hour, compared to 14 man-hours for the Zero. The complex engine demands skilled mechanics, but experienced maintainers are increasingly scarce as the war progresses. Spare parts become difficult to obtain as American submarines interdict shipping between Japan and resource areas. By mid-1944, Raiden serviceability rates average 42%. Of 10 aircraft assigned to a unit, typically only 4 are flyable at any time. Despite these difficulties, the aircraft proves devastatingly effective when it functions properly and pilots employ it correctly. The tactical doctrine emphasizes attacks from high altitude with speed advantage. Pilots climb to 9,000 or 10,000 meters, position above and ahead of bomber formations, then dive through at maximum speed, firing brief bursts before extending away. This hit-and-run approach maximizes the Raiden's strengths while minimizing exposure to defensive fire. Warrant Officer Sadamu Komachi, one of the most successful Raiden pilots, develops refined techniques. He positions 600 meters above bomber formations and 1,000 meters ahead of their course as bombers approach. He rolls inverted and pulls into a 60 to 70 degree dive, building speed to 600 to 650 kilometers per hour at 400 to 500 meters range. He opens fire with a 2 to 3 second burst, aiming for engines or fuselage center section. The combination of high closing speed and concentrated firepower frequently destroys bombers with single attacks. Komachi's success depends critically on aircraft reliability. When his engine functions properly, he executes attacks effectively. When mechanical problems develop, often without warning, he must abort missions or risk death. Between November 1944 and March 1945, Komachi flies 47 combat sorties in Raidens. He claims 11 B-29s destroyed and 7 probably destroyed. He suffers 6 forced landings due to engine failures, 3 mid-air engine fires, and multiple instances of partial power loss. His survival depends partly on skill and partly on fortune. Other pilots proved less fortunate. Lieutenant Junior Grade Yoshio Fukui forces lands his Raiden after engine failure during takeoff on February 4, 1945. The aircraft crashes inverted and burns. Fukui dies from injuries 3 days later. Ensign Takeo Shibata's engine explodes during combat on February 19, 1945. He attempts to bail out, but the aircraft enters an uncontrollable spin. Impact occurs at 800 kilometers per hour. Petty Officer Masao Ida successfully forces lands after cylinder head failure on March 9, 1945, but his aircraft is written off. These incidents repeat across all units operating the Raiden. The aircraft's combat record shows both capability and limitation. Between December 1943 and August 1945, Raidens claimed 276 enemy aircraft destroyed. American loss records confirm 132 B-29s, B-24s, and carrier aircraft destroyed by fighters matching the Raiden's description in areas where Raiden units operated. The disparity reflects overclaiming common to all air forces, but the confirmed kills demonstrate genuine effectiveness. 132 heavy bombers destroyed represents significant achievement. This success comes at severe cost. Of approximately 476 Raidens delivered to operational units, 291 are destroyed or written off. Combat losses account for 109 aircraft. Operational accidents, primarily engine failures, destroy 123 aircraft. Training accidents eliminate 37. Weather-related losses total 22. For every 2 enemy aircraft destroyed, the Japanese lose 1 Raiden. This exchange ratio proves strategically unsustainable. American production delivers approximately 1,000 heavy bombers monthly by mid-1944. Japanese production of all fighter types combined averages 1,700 aircraft monthly during the same period, of which only 40 to 60 are Raidens. The arithmetic guarantees defeat. Japan cannot maintain numerical parity regardless of individual aircraft effectiveness. Moreover, the Raiden's specialization limits its utility. The aircraft excels at intercepting high-altitude bombers, but performs poorly in other roles. Its heavy wing loading and limited agility make it vulnerable to American carrier fighters like the F-6F Hellcat and F-4U Corsair. Its short range prevents escort missions. Its high landing speed of 168 kilometers per hour causes frequent accidents on damaged runways. By late 1944, many airfields in Japan and occupied territories suffer bomb damage, making safe Raiden operations difficult or impossible. Several variants attempt to address deficiencies. The J2M3 introduces the Kase 23A engine with improved supercharging and water methanol injection for emergency power. This increases output to 1,820 horsepower, but does not solve reliability problems. The J2M4 mounts two 30mm Type 5 cannons, replacing two of the 20mm weapons. This increases striking power but reduces ammunition capacity to 60 rounds per gun, sufficient for approximately 6 seconds firing. The J2M5 features improved aerodynamics and a bubble canopy for better visibility. Only 38 J2M5s are completed before war's end. None of these variants fundamentally transform the aircraft. The Raiden remains what it was designed to be, a specialized high-altitude interceptor optimized for specific mission parameters. When employed within those parameters against appropriate targets, it performs effectively. When circumstances demand versatility, range, or reliability, it fails. Production totals reflect these limitations. Mitsubishi manufactures 476 Raidens between December 1943 and August 1945. This compares to 10,430 Zeros produced during the same period. The Navy clearly prioritizes quantity and versatility over specialized capability. Resources allocated to Raiden production might have produced an additional 350 Zeros, which could operate from carriers, escort bombers, perform ground attack, and intercept at medium altitudes. The Raiden does none of these things. This production decision reflects realistic assessment of strategic requirements. By 1944, Japan faces threats at all altitudes and ranges. American fighters sweep Japanese skies at altitudes where Raidens operate poorly. American bombers attack from high altitude, where Raidens excel, but also from medium and low altitude, where they struggle. The Navy needs fighters capable of addressing multiple threats, not specialized weapons effective against limited target sets. The Raiden's design philosophy itself proves problematic. The concept of sacrificing range and agility for climb rate and firepower works only when enemies cooperate by appearing at predictable times and altitudes. American operations become increasingly unpredictable during 1944 and 1945. Carrier task forces strike randomly, giving little warning. B-29 raids vary altitude and approach routes. Fighter sweeps occur at times when bombers are not present, catching interceptors during landing or refueling. These operational patterns negate the Raiden's advantages. An interceptor that climbs rapidly but remains grounded due to engine problems provides no defense. An interceptor with devastating firepower but limited ammunition proves ineffective when enemy fighters avoid engagement until fuel and ammunition are exhausted. An interceptor optimized for high altitude proves useless when attacks occur at medium altitude. American pilots who encounter Raidens report mixed impressions. Lieutenant David McCampbell, leading fighter ace of the United States Navy, describes an engagement on October 24, 1944. Intercepted formation of Jacks, Allied code name for Raiden, attempting to attack our bombers. They climbed very fast, probably faster than our Hellcats could match. But once we engage, they couldn't turn with us. We got on their tails and they couldn't shake us. Shot down 3. The others ran for cloud cover. Dangerous if they get altitude advantage. Easy targets if we catch them at our altitude. This assessment captures the Raiden's operational reality. Superior in specific circumstances. Vulnerable when those circumstances change. The aircraft represents peak performance within narrow parameters, rather than adequate performance across broad requirements. Japanese pilots express frustration with these limitations. Petty Officer Saburo Sakai, one of Japan's highest scoring aces, flies the Raiden operationally during early 1945. His assessment: the Raiden climbs like a rocket and hits like a sledgehammer. It also breaks like glass. The engine quits without warning. The controls are heavy, exhausting to fly for long periods. Visibility is poor, making formation flying difficult. It's an excellent aircraft for a 5-minute engagement when everything works. Most engagements last longer, and things usually don't work as designed. I prefer the Zero. It may be slower and more lightly armed, but it gets me home. This preference for reliability over peak performance appears throughout pilot accounts. The psychological burden of flying aircraft with questionable reliability affects tactical decisions and combat effectiveness. Pilots flying Raidens conserve fuel more carefully, avoid prolonged combat, and disengage earlier than they might in more reliable aircraft. This conservatism reduces overall effectiveness despite the aircraft's superior specifications. Technical analysis of surviving Raidens reveals the source of many reliability problems. Japanese metallurgy during the late war period produces inconsistent materials. Engine components manufactured to identical specifications exhibit varying quality. Cylinder heads crack due to internal flaws in casting. Valves fail from inadequate heat treatment. Bearings wear prematurely from insufficient hardness. These quality control failures stem from resource shortages, inexperienced workers replacing skilled personnel drafted into military service, and deteriorating manufacturing equipment that cannot be repaired or replaced. The Raiden suffers disproportionately from these problems because its high-performance engine operates at extreme stress levels. The Kasei 23 engine runs at higher cylinder pressures and temperatures than earlier Japanese engines. This leaves less margin for material defects. A cylinder head casting flaw that might cause no problems in a lower stressed engine results in catastrophic failure in the Kasei 23. The design assumes manufacturing quality that Japanese industry can no longer consistently deliver. By mid-1945, the strategic situation renders the Raiden's mission obsolete regardless of technical performance. American forces occupy Okinawa, placing fighters within range of Japanese home islands. B-29 raids now include fighter escort by P-51 Mustangs flying from Iwo Jima. The concept of unescorted bomber formations vulnerable to interceptor attack no longer applies. Raiden pilots now face not only heavily armed bombers, but also escorting fighters specifically tasked with destroying interceptors. The results proved devastating. On April 7, 1945, 38 Raidens from multiple units intercept a B-29 formation escorted by 112 P-51s over Tokyo. The Raidens destroyed 3 B-29s. The P-51s destroyed 22 Raidens. Exchange ratio, 7.3 to 1 against the Japanese. This engagement typifies late war combat. Japanese interceptors, optimized for attacking bombers, proved nearly helpless against dedicated escort fighters with superior performance and numerical advantage. Final combat operations involving Raidens occur in August 1945. By this time, fewer than 40 operational aircraft remain across all units. Fuel shortages limit sorties. Pilot losses have eliminated most experienced flyers. New pilots receive minimal training before assignment to combat units. The few Raidens still flying achieve occasional successes but cannot affect overall strategic outcomes. Total wartime production reaches 476 aircraft. Combat claims total 276 enemy aircraft. Confirmed losses to all causes, 291 aircraft. Approximately 130 remain in various states of repair when Japan surrenders. Most are scrapped. A handful survive in museums. The Raiden represents a common pattern in late war Axis aircraft development. Sophisticated designs optimized for specific scenarios that rarely occur operationally. The aircraft excels at high altitude interception, but circumstances increasingly demand versatility. It carries devastating armament but suffers reliability problems preventing consistent availability. It achieves high performance but requires operational conditions that enemies actively prevent through tactical adaptation. These contradictions doom the aircraft to strategic irrelevance despite tactical effectiveness. When it works properly and encounters appropriate targets under favorable conditions, the Raiden performs brilliantly. These circumstances occur too infrequently to justify the resources invested in development and production. Alternative approaches might have produced superior outcomes. Resources allocated to Raiden development and production could have improved zero-engine reliability or developed better pilot training programs. 476 Raidens represent approximately 13,000 man-years of engineering and manufacturing labor applied elsewhere. This effort might have produced more strategically significant results, but such calculations require hindsight unavailable to decision-makers in 1940. The Navy's requirement for a high-altitude interceptor reflected reasonable anticipation of future threats. The design specification emphasized attributes necessary for countering those threats. Mitsubishi produced an aircraft meeting the specification as well as industrial and technological constraints permitted. That the resulting weapon proved less useful than anticipated reflects the difficulty of predicting future operational requirements rather than failure of engineering or planning. The Raiden's legacy lies not in its combat record but in what it reveals about specialized weapons in fluid strategic environments. Optimization for specific missions creates vulnerability to changing circumstances. Reliability matters more than peak performance when operations occur continuously under stress. Versatility provides greater strategic value than specialized capability. These lessons apply beyond aviation to all military technology development. Surviving Raidens exist in only a few locations. The Plains of Fame Air Museum in Chino, California displays a partially restored J2M3. The National Museum of the Pacific War in Fredericksburg, Texas exhibits components recovered from crash sites. The Kawaguchiko Motor Museum in Japan possesses the fuselage section of a J2M5, no complete. flyable example exists anywhere in the world. At 11:27 hours on January 9, 1945, Warrant Officer Kamachi launches to intercept B-29s. His Raiden climbs rapidly, delivers devastating firepower, and destroys 2 bombers. It also suffers damage requiring complete engine replacement. This engagement summarizes the aircraft's entire operational career. Brilliant performance compromised by marginal reliability. Tactical success overshadowed by strategic irrelevance. A sophisticated weapon perfectly designed for a war that never quite occurred, as planners anticipated. The Mitsubishi J2M Raiden was Japan's thunderbolt, striking from above with tremendous force. Like actual lightning, it appeared suddenly, struck powerfully, and disappeared quickly. Unlike lightning, which strikes reliably during storms, the Raiden functioned inconsistently, broke frequently, and succeeded only when circumstances aligned precisely with its narrow capabilities. This was not the weapon Japan needed during its desperate final years. It was the weapon Japan designed when victory still seemed possible and specific threats could be isolated and countered. By the time the Raiden reached operational service, Japan needed not specialized interceptors but versatile fighters in overwhelming numbers. The Raiden provided neither. It remains a monument to the danger of optimization, designing the perfect weapon for the specific war you expect rather than the adaptable weapon for the war you actually fight.